Welcome to my class. I'm Drew Collop. In today's class, we're going to talk about application of percents to the laboratory. In a much earlier lecture, we reviewed the basics of percent. Again, percent means per 100. We use a proportionality statement to solve that. And when working with percents in the lab, I would like you to use a proportionality statement. It is the quickest way to calculate values in the lab. As you can see, we have 100 on the bottom, we have the percent on top. 7% would mean 7 over 100. We have the part compared to the whole. And this will vary depending on the situation. In this lecture, I intend to go over many of the different applications of percents in our labs, with the exception of solutions. That will be a whole other lecture on its own. Let's look at our first one, percent change. With this, we can compare two quantities together. So we can say the price of gas rose 3% over last week's price, the weight of the new iPhone decreased by 20%, unemployment dropped by 1.2%, or tuition has increased 80% over the past 20 years. So in all these situations, we're comparing one quantity to a quantity at a different time. Percent change is a way to represent a change over time. So we're going to compare two numbers and see how they change from one time to another. We'll have the original value and a new value. Please note the denominator is always the original value. So here's our proportionality statement. Remember, a proportionality statement is two fractions that are equal to each other. Please note, we have the original value on the bottom and on the top. We have the new value here. So we take the new value, we subtract away the original value, and we divide by the original value. Some people like to put absolute values on there, telling you it is always going to be a positive change. I prefer to leave those values out. I like to know whether the change is going up or going down. If you get a positive percent change, your value is increasing. If you get a negative percent change, your value is decreasing. Let's now look at some examples. Find the percent change when a quantity changes from 29.3 to 57.6. So this is your original. This is your new. So we're going from this value to that value. What I'll say, my percent is what I'm looking to solve. That is x. X over 100 equals my new value, 57.6, subtract my original value, divided by the original value. Subtract those values away. We can then cross multiply. Divide both sides by the coefficient in front of x to get rid of that. And we are left with let's round off to proper number significant digits. This is important here. Notice we are starting with subtraction. With subtraction, we go to the fewest number of decimal places. Each of these has one decimal place, so this will be rounded to one decimal place. We are then multiplying and dividing. This has 3 digits, this has 3 digits. Please note, this value is an exact value, meaning there's an infinite number of significant digits. As a result, we'll round this final answer off to 3 significant digits. Final answer. Notice it is a positive percent change, meaning the value has gone up by 96.6%. Look at the question. It goes from 29.3 to 57.6, so it is clearly increasing. Let's look at another example. The temperature in a building fell from 21 degrees Celsius to 19 degrees Celsius. Find the percent change. We'll call this our unknown x. X over 100 equals, this is my original, this is my new. 19.0 minus 21.0 divided by 21.0. X over 100 equals negative 2.0 over 21.0. Cross multiply. Divide both sides by 21 to isolate x on its own. Significant digits now. Remember, this is an exact value. We're subtracting, going with the fewest number of decimal places. This has 1 decimal place. Now we're multiplying and dividing. This has 3, this has 2. So we'll round this off to 2 significant digits. We put the percent sign at the end. So the answer to this is, the percent change is negative 9.5%. Now notice, we've gone from 21 to 19. So the negative sign indicates it has decreased. Let's look at one more example together. A student is earning $425 per week working in the SSF office. This is the Seneca Student Federation office. They receive a 14% increase in their pay. What is the new salary? This is a percent change. However, we're asked to solve what the new salary is going to be. That's going to be my x value. This is my new value. This is my original salary. This is my new salary. My percent change is 14%, which is 14 over 100. Let's now build that equation. 14 over 100 equals my new salary, subtract the original salary, divided by the original. The denominator is always the starting point. Now you can see we have to rearrange. Please note, it increased. As a result, that is a positive number, as opposed to a negative number. Now let's rearrange and solve for x. 14 divided by 100 times 425, we get swing the minus 425 to the other side, becomes positive. X is equal to 484.5. Significant digits now. We're dealing with money. With money, we always round off to 2 decimal places. As a result of a 14% increase, your salary's gone from $425 per week to $484.50 per week. This might be helpful. At many jobs, you get a certain percentage increase every year. When budgeting, it could be helpful to find out how much money you'll be making the following year. I'd like you now to try this practice problem involving percent error. The local electronics store has the TV you want 23% off. If the original price was $1,999.99, what's the new sale price? Let's say what's the price before taxes. Pause your video. Try this now. Here's your answer, $1,539.99. Let's take it up. So it's 23% off, meaning it's going down by 23%. This is the original price. I'm subtracting away the new price. I don't know what that is. Let's get rid of this denominator by multiplying this side by the denominator. Whatever I do to one side, I have to do the same thing to the other side. Minus 23 divided by 100 as a decimal. Equals x minus 1,999.99. Swing that over to the other side. Now notice I have not combined together these values just yet. because I want to show you something. X is equal to, let's take out a common factor from both these values. The common factor is, this is going to be negative 0.23 plus 1. X is then equal to 1 subtract 0.23 gives me 0.77 multiplied by the original price. X is equal to, round off for significant digits now. We're dealing with money, so we always round off to 2 decimal places. So your new sale price is $1,539.99 before tax. Please note, I use this method of pulling out a common factor so I could get this. Next semester, when you start dealing with exponential growth, you're going to do something just like this. I wanted you to see it first before you see it in your next math class. So this was using the formula for percent change. Let's now examine another percent. Percent error. So percent error refers to the accuracy of your measurements. Once again, you're comparing things. You're comparing the difference between a measured value and a theoretical or accepted value. Here you can see the formula. Percent over 100 equals the measured value minus the accepted value divided by the accepted value. So once again, you can see we have the accepted value on the top and the bottom, and here we have the measured value inside. Let's try a problem. Working in the laboratory, a student measures the density of a piece of pure aluminum, and they measure it at 2.85 grams per centimeter cubed. From the literature, we know the accepted value should be 26.99 grams per centimeter cubed. What is your percent error? This is my unknown x. X over 100 will give me my percent error. My measured value is right here, and my accepted value is right here. Let's plug those values in. Now we solve. Notice we sub in those units. We can combine those together because they'll have the same units. Let's do that now. As a result of having the same units on the top and the bottom, you can see the units cancel out. That's why they don't appear in the final answer. We will then cross multiply. And divide both sides by my coefficient in front of x to isolate x on its own. Those cancel out. I'm left with x is equal to significant digits now. I'm subtracting. I have 2 decimal places. I have 3 decimal places. So I round this off. This would be rounded off to 2 decimal places. I'm then multiplying and dividing. This has 4. This would be an exact value. This would have 2 significant digits. As a result, I round this off to 2 significant digits. X is approximately equal to 5.6%. Notice I haven't put in the absolute values. In some classes, they say when you work with percent error, it's always going to be a positive number because you put absolute values on the top, right here and here. In the laboratory, I prefer not to do that. I would like to know which direction I'm off, either in the positive direction or the negative direction. This can be quite helpful when calibrating equipment. Do you adjust it one way or the other way? As a result, I never work with absolute values when calculating percent error. But please consult your instructor or supervisor for the individual experiment and what they would like. Now here's a problem from a tissue culture lab. In tissue culture, you grow mammalian cells outside the body. This can be quite helpful because we can run experiments on cells without having to work with whole organisms. As well, we get direct access to the cells. If we want to do experiments on the liver, we can grow liver cells up and use our drug on that. Otherwise, getting the drug of interest to the liver in a whole organism can be difficult. Many metabolic processes can change the structure before it gets to the liver. You can see we have a 24 well plate here, 24 individual wells. What we do is we place the cells inside, we let them grow for a bit, we add our drug, and then we harvest the cells. We can extract DNA, RNA, proteins, metabolites, anything of interest, and analyze that. As a result, setting up these plates is very important. Let's say you require a 5 ml solution with a certain concentration of cells, 2.00 times 10 to the 5 cells per ml. In the lab, we have special machines that count cells. One is called the Coulter counter. We can use this to quickly and accurately count our cells. When we count our cells, we realize we have 7.78 times 10 to the 8 cells per ml. In the laboratory, once you get the concentration you have, you'll perform a serial dilution to achieve a desired lower concentration. Serial dilutions will be the topic of another lecture. In the end, we count our cells and we determine we have 1.81 times 10 to the 5 cells per ml. In many laboratories, you must be within 10% air, or sometimes 5% air. For this question, we'll say you must be in 10% air. The question is this acceptable, or do you have to repeat the experiment? Let's do the math now. We want to know what our percent air is. We have our measured minus the accepted divided by the accepted. My accepted value is what I asked for. My measured value is what I diluted down to. Let's sub those in and solve for x. We've subbed in our values. Now let's solve for x. Notice we have 10 to the 5 on the top and 10 to the 5 on the bottom. They can cancel each other out. Let's cross multiply and solve. Divide both sides by my coefficient in front of x to isolate x on its own. Significant digits now. I'm subtracting, so I go with decimal places. This would be rounded off to 2 decimal places. When multiplying or dividing, this has 2 significant digits, this has 3 significant digits. So I'd round this off to 2 significant digits. Notice it is already in significant digits. Therefore, that's the final answer. Negative 9.5%. Notice we are within the 10% range, just barely, so we do not have to repeat this experiment. In addition, our percent error it states is negative. This tells us we overshot. I wanted 2 times 10 to the 5. I overshot and got 1.8 times 10 to the 5. Knowing this can help better your technique the next time you have to perform this experiment. What you want to do is go back and look at your protocol and see if you could improve that along the way. If you're in the biotechnology program, you will have me in upper semester for tissue culture. The final lab exam in this course is practical. I will give each student in the class a different final concentration. You will take your cells, you will do a serial dilution down to that. You will then count the number of cells you have. You'll calculate the percent error, and your final mark will be based on how close to 0% error you have. Skills are very important. Let's now examine percent yield. As we did stoichiometry, we could calculate theoretically how much of a chemical we should get. However, the actual amount of chemical you're going to get is always going to be less. Your percent yield indicates the difference between your actual amount and the theoretical amount you calculated on paper. No chemical reaction is 100% efficient. So if you state you had 100% yield, you are mistaken or you are lying. Please be aware of that. That is a common issue we have with some chemistry assignments. Students say that they had 100% yield on their chemical reaction. This is not true. Again, they're either mistaken or they didn't do the work and they're lying. Once again, we can use a proportionality statement to solve this. The percent yield is your actual amount divided by the theoretical amount. Remember what I stated, you'll never have 100% yield. So the actual amount you're going to get will always be a lower number than the theoretical amount. As a result, the actual is always on the top. Let's try some examples. The chemical reaction of hydrogen and oxygen, you're expected to produce 35.0 mils of water. This is what you theoretically calculated using your stoichiometric calculations. When you do the reaction, you collect the water and you measure it's only 34.5 mils that you received. The question is what is your percent yield? That's your unknown. We will use X as our unknown. Theoretically, we should have obtained 35.0 mils of water. However, we actually obtained 34.5. Let's plug those in. Notice, same units on the top and the bottom. They cancel each other out. Cross multiply. Divide both sides by the coefficient in front of x to isolate x on its own. Significant digits now. I have 3. I have 3. This would be an exact value. So I'm going to round this off to 3 significant digits. So x is approximately equal to 98.6%. So your percent yield for this reaction is 98.6%. This is very high. Just remember, we place the actual over the theoretical. Let's do one more example together. You perform an experiment and 24.6 grams of sodium chloride are produced. The percent yield from your reaction was 94.5%. The question is, based on your calculations, how much NaCl would you expect to get? So here I've given you the percent yield. I've given you the actual amount. I'm asking you to solve for the theoretical amount. So 94.5%, 94.5 per 100 is equal to actual. When I did the experiment, I got 24 grams. I want to know theoretical. Cross multiply. And divide both sides by the coefficient in front of x to get that on its own. Those cancel out. Notice I'll be left with grams as my final answer. Significant digits now. I have 3. I have 2. This is an exact value. I'm going to round this off to 2 significant digits. As a result, x is approximately equal to 2.5 grams sodium chloride. So notice in this reaction, we can back calculate. This can be helpful when manufacturing chemicals in a laboratory environment. If I need 2.4 grams of a chemical and I know the percent yield is 94.5%, I based all my calculations on producing 2.5 grams of sodium chloride. Here's a practice problem based on that exact situation. You work for a chemical company. A customer has contracted your company to produce 150 kilograms of a chemical. That chemical reaction is known to have a 56.0% yield. So we want to calculate how much theoretically we need to produce. We don't want to produce too little because then our customer won't get what they asked for and they'll be upset. We don't want to produce too much because it'll lower the company's profits and your supervisors won't be happy. I would like you now to calculate how much theoretically you should produce to actually produce 150 kilograms, given a reaction has a percent yield of 56.0%. Try that now. So work it out. 56%. Actually, what I want to make, 150 kilograms. I don't know how much theoretically I want to make. Again, that's going to be in kilograms. You can see kilograms cancel out. Cross multiply. Divide both sides by 56 to isolate x on its own. Significant digits. 3, 4, that's an exact value. Going to round this off to 3 significant digits. It's approximately equal to 268 units, kilograms. Guess I didn't have to cancel it out. It's going to be X kilograms right there. Up to now, we've talked about percent change, percent error, percent yield. We're now going to talk about percent concentration. Percent concentration is perhaps the most important applied percent for you to understand. When we have mixtures, we have a solute. This is the substance being dissolved. We have the solvent. This is the substance doing the dissolving. And we have total solution. This is the sum. We're adding up all the solutes and the solvents. So we take our solute, we take our solvent, we add them together, we get our total solution. This concept is very important. Notice the proportionality statement, 4% concentration. We have percent concentration, that's percent, so it's 100. We have the amount of solute on the top, and on the bottom, what do we have? The amount of total solution on the bottom. Notice, solvent is not in the denominator. That is a common mistake students make. They put solute over solvent. No, this total solution is solute plus your solvent. That's a very important fact. And if a student is going to make a mistake, it's going to be because they wrote solvent on the bottom, not total solution. Let's look at some examples. Suppose that 20.0 grams of sugar are dissolved in 165 grams of water. Calculate the percent concentration. I don't know what the percent concentration is. That'll be my unknown. I'm taking 20.0 grams of my sugar, and I'm going to dissolve that into water. Be careful here. Again, this is a common mistake students make. They write that and they work it out. But I'm adding 165 grams of water to my 20 grams of sugar. So I have to add them together. Very important. This will give me total solution. So it's solute divided by total solution. It's going to be grams on the top and grams on the bottom. As a result, they cancel out. Cross multiply. Divide both sides by 185 to isolate x on its own. X is equal to significant digits now. I have 3 digits. Now when I'm adding these up, I go with the fewest number of decimal places. This has 1 decimal place. This has no decimal place. It is to the nearest ones. So if I was to round this off, it would be rounded off to the nearest ones. In doing that, I have 3 significant figures. I have 3 significant figures. So this should be rounded off to three significant figures. X is approximately equal to 10.8. Units, this is going to be percent. We're dealing with a weight over weight. Notice it's grams in the numerator and grams in the denominator. As a result, we write weight over weight, like a little fraction. 10.8% weight by weight. It tells you that we have percent concentration and it's grams over grams. Let's try the next one. Calculate the mass of salt that must be dissolved in water to prepare this many grams of a 7.00% solution. Here I have my percent, 7.00% per 100. What I want to know is the mass of my solute. Notice it says we dissolve in water to prepare 5.00 times 10 to the 2 grams, and this would be a total solution. This is quite a common technique in the laboratory. We add the amount of powdered chemical we need, and then we top up, meaning we add water until we reach the final desired volume. So what I don't know is what the mass of the solute is. We can now work that out. Cross multiply. Divide both sides by 100. X is equal to 35. What's our units going to be? It's grams here. This will be grams. Significant digits. I have 3. I have 3. This is an exact value. So this would be 3 significant digits. So I'd round this off to 35.0 grams of my salt. Final answer. Notice this would also be percent weight by weight. I have grams on the bottom, and I asked for mass here, so this would be grams on the top. So this would be percent weight by weight. We have a practice problem here, going back to our lecture on kitchen conversions or kitchen chemistry. Calculate the percentage of butter in an icing recipe that requires 80 ml of butter, 70 ml of milk, and 650 ml of icing sugar. Try that now. Let's take it up. So I want to know the percentage. That's my unknown. X over 100 is equal to. Again, please set these up as a proportionality statement. What do I want? I want to talk about butter. That's the solute in question. How much butter is there? 80.0 mils of butter. When I add them all together, that'll be my total solution. So I have to do my 80 mils of butter plus my 70 mils of my milk plus my 650 mils of my icing sugar. Again, we have total solution and we have a solute. Here I want to talk about butter. If I was asking for the concentration of milk, my numerator would be different. If I was asking for the concentration of icing sugar, my numerator would be something else. However, the denominator would remain the same. Let's solve this now. Notice I have mils on the top and mils on the bottom, so they'll cancel each other out. Cross multiply. Divide both sides by my coefficient in front of x to isolate that on its own. 80 divided by 8 is 10. Significant digits now. I have 3 digits. I'm adding these up, so I go with the fewest number of decimal places. Notice this has 1 decimal place, 1 decimal place. This has no decimal place. Technically, the 0 is just a placeholder, so we'll say that's rounded off to the nearest tens. So if I was to round this off, it would be right here, giving me 2 significant figures, 3 significant figures. This is now rounded off to 2 significant figures. As a result, 10% is the percentage. Now please note, this is different from before. We have milliliters on the top and milliliters on the bottom. As a result, we write in brackets 10% volume by volume. So this buttercream icing would have 10% volume by volume butter. So in today's lecture, we've looked at the application of percentages in our laboratories. We've examined percent change, percent error, percent yield, and now percent concentration. Our next lecture will focus only on concentrations. We'll look at percent concentration weight by weight, weight by volume by volume, parts per million, and molarity. That's all for today. Until next time.